So today actually we will start from uh, a our definition and example. Last time in the last class we gave the digital system. So we have learned that how to describe any digital system. It could be described in terms of that difference equation, or it could be described in terms of the what is called the block diagram or signal flow graph or a schematic. Different names it has actually, but basically the same thing. So basically it has mainly two types or two modes of representation. So they are obviously equivalent to each other. So basically both of them actually giving the same information, but there is a subtle difference if you minutely follow their style of representation or mode of representation. So you can find a basic difference between the two, which you have already pointed out in the last class. So the actually your different the equation form, the representation in the terms of the mathematical representation or in terms of the equation or expression, actually is a very it's a concise. Okay, so the adjective concise is actually associated or applicable for this kind of representation, where the diagram representation or the signal flow representation, for that you can use the adjective like precise. So it's a precise. Specifically it is pointing out that what is the input, what is the output, how the signals are flowing from input to output and via which path, and so on and so forth. So all these things are actually explicit, actually very much clear there. It is explicitly described over there. Now, so that means I can say that just a minute, just let me share the screen first. Can you see it? No. Now?
Yes, sir.
Yes. So basically that was the system I'm talking about, this example. So this is basically a digital system, and this system actually that you see that it handles a digital signal. It operates. This is the operation is being done within this box. So there are different within this system. There are different subsystems, or you can say different components. So this handle, this XN, this digital signal operates on it, and you are giving or producing another signal. Obviously, that is also digital in the form, and but of course in some better than what we had at the beginning. Obviously, or you can say in some more desired form. What we obviously there is a specific task to perform. So that means we want something in it. Just a minute. So we desire something, so we are getting that desired signal actually, which is of course in a better form or much desired form than what we had at the beginning. So this is just an example. Okay, so it's in general I'm talking, but this is an example just to substantiate the definition. And in this system, if we follow basically the same actually difference, these two are the different types of representation as I've already mentioned. And this equation or mathematical form or expression actually gives you what is called the difference equation, but its analogous form for the continuous time domain will be the differential equation. And this difference equation, that here you have the xn, you have the xn minus 1, you have yn, you have yn minus 1, and so forth, so on and so forth. So this is particularly for example, but in general you may have different terms like that. Okay, different samples like that. So it is basically the as I mentioned, the analogous or counterpart of the differential equation. Okay, so any dynamic system actually could be described by this kind of difference equation in the digital domain, and of course the differential equation in the analog domain. Similarly, for the analog domain, analog or the continuous time signal domain, there also you can represent with this whole dynamic system with this kind of block diagram as well. So there, this instead of summation, there will be integration, something like that. And here also the delay and all these stuffs are possible. So there actually you have to use the Laplace transform. Here the Z transform, there the Laplace transform. That is the conceptually they are same. Just a little bit difference between the this individual as far the individual blocks are concerned. Okay, so difference. Anyway, so it is basically this diagram representation is actually basically, or the schematic representation is basically, it tells you about the hardware as well as about the software. So as I've already mentioned that in terms of hardware, suppose if anyone asks you that in terms of hardware, how many numbers of different elements are required? Suppose, for example, delay elements. Okay, as I mentioned, there are different elements, components. So how many number of components are in total required? Specifically speaking, suppose the delay element. So here you have one or two delay element, one and two. So two delay elements are required. Similarly, you have just see you have some multipliers. Now all these are the scalar multipliers. Please note it. So the 1, 2, 3, three multipliers are required for to realize this system. Similarly, you have two summer or adder. These two are also required. So in terms of hardware, you can realize this thing. Okay. Similarly, this thing is also you can find out from here, but from here it is very straightforward, very easy, because everything is so precisely mentioned, so specifically mentioned. So it is very easy to understand actually. So now in terms of software also, it shows that the things are that which things are getting multiplied, okay, by what, and which signal to be retrieved, okay, like here or here, what and storage and all those things. Actually storage means here actually this kind of things is equivalent to storage actually. So delay element kind of storage. So these things could be implemented by program. Okay, this in a program you will learn in your, I think in the 6th semester there is this core subject that you will learn how to represent this in this kind of systems, even the very complicated systems also in terms of your software program. That is possible. Anyway, so this is all about the system. Today we will talk little bit about the sampling process. Sampling process. You have already have some idea in my initial classes. I have already introduced some idea about the sampling and quantization, etc. So here I will try to elaborate the things in more details. So sampling process, you know that your suppose if we have a signal like suppose cos omega naught t in a continuous time domain with the phase suppose phi. So this is capital omega naught, and I'm not talking about the amplitude and all those stuffs because I'm not concerned about that. So you can put a or something like that. That is same thing. Nothing is going to change for that. But again, after sampling and obviously the AD conversion, this is the symbol. Already I have introduced this in your class, one of your classes possibly. This is sampling. This is sampling, and this is AD conversion. A to D conversion is done. So after that, what you get basically this signal, or the representation actually changes. So the representation becomes, that n omega 0 plus the phi, suppose this thing. And where that omega 0 is the digital frequency, that it doesn't have any unit. It is basically the ratio of same type of parameters. So it is basically unitless, and sometimes it is called a normalized frequency as well. So people say it is expressed in radian, because after all it's an angle, but radian not per second. So omega naught is basically is represented like this: 2 pi f naught comes from here, divided by fs. You know that quite well. I've already discussed it. So fs is actually the sampling frequency. So the digital frequency is actually related to the sampling frequency, because after all, after sampling I'm getting, so obviously that must be some relation. So, and this is the relation. Anyway, so this is after sampling and AD conversion. But in this, at this point, I want to mention one thing, that in general, we do not show this AD conversion. Even in most of the books, they do not show this AD conversion, because the reason is AD conversion means actually you have converted the signal in a purely digital form. Okay, but you know, to get any pure digital signal, you have to first convert it to discrete time. You know, first discrete time, then you have to discretize the amplitude by the process called quantization, you know, and then only you can say yes, it is in a purely digital domain. And coding, those part are different thing. So just I'm talking about the representation, of signal representation in the form of signal, or how to represent in terms of signal, not in terms of beats and other things. So that is for related to the coding. Now, anyway, so as far as the mathematical techniques and expressions are concerned, now it doesn't actually matter whether you are talking in terms of the purely digital signal or in terms of the, you know, discrete time signal. Actually, the same thing. That is why I actually ignored this amplitude. Okay, just you see here, I am not bothering about the amplitude of the original analog time continuous time domain signal, or okay, how after quantization the level of change, because after all those will be represented by beats. So I am not concerned about that. I am just concerned about the mathematical form. Okay, so here, even if I don't write a do the conversion just after sampling, means suppose you have not applied the step of quantization. Okay, the quantization process is not applied on the signal samples version. Then also that means the signal is only discretized in the time domain. So there also you can apply the same process or same mathematical treatment as you can apply for a purely digital signal. So it hardly matters as far as the mathematical techniques and treatments and operations are concerned, whether you are doing the quantization or not. That means whether you are dealing with the purely digital signal, that means after quantization, or you are dealing with a discrete time signal, that means no quantization is done, that means just after sampling, it doesn't matter. Getting the point? So because it arguments wise, basically they are same as far as the signal representation is concerned. Okay, I'm not talking about in terms of the beats and all those stuffs. So this is suppose conversion. After this conversion, now we know what do you know from our sampling theory, that is Nyquist rate. We know that your f naught is this the signal frequency or maximum signal frequency, sometimes people say. So f naught, that should be you know, that fs by 2, or in other words, the sampling frequency should be twice the maximum frequency contained within this signal. You know that already. So the sampling frequency has to be more than that, if not at least equals to that. Okay, and if it is less than that, then you are in danger. So now the question is, it is okay, we know the relation, we know the theory, it's okay. But just to enrich our idea, so here I want to mention one numerical example, just to see what actually happens if this is not the case. If one violates, if one doesn't obey this criterion, this rule, then what is going to happen? Yes, we have already told you that there will be distortion. You cannot recover the original signal. But yes, that is true. We understand the theory, but a small numerical example will basically illustrate the fact. Now, suppose you have, let's say, a small example for you actually. Suppose cos 6 pi t, you have one signal 6 pi t, okay, in the continuous time domain, as you can understand. Another second one is suppose cos 14 pi t, and the third one is suppose cos 26 pi t. Okay, now you know that from this representation, you know that the frequency, if you say for this signal, what is the frequency? Frequency is 3 hertz, for this 7 hertz, and for this 13 hertz. So for the time being, just to see, I'm just avoiding this phase factor, okay, because it hardly matters, okay, to make that, to keep the thing simple actually. Now these are the sampling frequencies corresponding to 3 different signals. Now suppose the sampling interval sampling interval বা কি বলে sampling period t equals to suppose 0.1 second. Suppose this implies, just tell me what is the value of fs. If this is t, then what is the value of sampling frequency? Anyone? Just tell me.
So 2 pi by t.
ভ্যালুটা বলো sampling frequency value কত হবে? If sampling period is 0.1 second, then what is the value of sampling frequency?
10 hertz.
10 hertz. Good.
10 hertz.
10 hertz. Okay, 10 hertz. This is the sampling frequency. Now just if you compare these 3 frequencies with this sampling frequency, just to compare, now obviously 10 as per this is the relation, you have to follow this, you know that, but deliberately I am just I'll violate it and will show what could happen, what is the possible outcome. Okay, so anyway, so this 10 hertz is, of course, this is a correct sampling frequency for the first signal. Fine, because twice, look at this, twice 3 2 6, so that is less than this, it's okay. But what about the second signal? If you sample with this frequency, the second signal, it has frequency 7 hertz, so 7 into 2 is 14, so which is more than this? Okay, similarly 13 hertz, 13 into 26, so that is also more than this. So actually from if you know the criterion, so from that you can straightforward say yes, for this signal it is okay, but for these 2 signals this sampling frequency is not adequate. Fine, but still we, as I mentioned, we will deliberately sample, we'll intentionally sample this thing. Let's see what happens if we sample. So forcefully we are going to sample, so let's see what happens. Okay, now if you sample, suppose if you sample this with this frequency, this sampling frequency, let's see what happens. আচ্ছা, এটা করলে কত পাওয়া যায়? From this what comes? এটাকে যদি তুমি স্যাম্পলিং করো কি পাবে? এখান থেকে এইভাবে লিখছি, জাস্ট মিনিট, এখান থেকে আফটার স্যাম্পলিং এখান থেকে কি আসছে, এখান থেকে কি আসছে, based on this formula. So you can write from here, you will get cos 10, তো এটা পাচ্ছ হচ্ছে 0.6, তাই তো, 6 pi n. From here 1.4 pi n. From here cos 2.6 pi n. These 3 are the representation in discrete time or digital, whatever you say, in domain. Fine. Now as far as the first signal is concerned, there is no problem, it's okay, it's okay, it's okay. But the second signal, after discretization, of course, this second or after sampling, of course. So this cos 1.4 pi n could be written as cos 2 pi n minus 0.6 pi n. Am I correct? Now, which is nothing but cos কত? 0.6 pi n. Got it? Similarly, if you represent this, it could be represented or could be rather written cos, it is minus, it is plus 2 pi n plus 0.6 pi n, which actually reduces to cos 0.6 pi n. Now you just look at these three signals ultimately. They are basically same. So these three signals become indistinguishable. Everyone got it? These three signals after sampling become indistinguishable. This is what actually inadequate sampling frequency does. If you don't follow Nyquist criterion, then you may land in danger, and that is the thing. So this sampling, as you know, that this was not adequate for this and these two signals to get sampled, but still we forcefully did, and as a consequence, what we got is got the three indistinguishable signals in the digital domain or discrete time domain. Now the 7 Hz signal, as if this one, the 7 Hz signal actually pauses or behaves as if it is a 3 Hz signal. Look at this, there is no difference. Similarly, this 13 Hz signal, originally it is 13 Hz signal from the point of view of analog signal. Originally it is a continuous time domain analog signal. So the 13 Hz signal also behaves that or poses like it is also this 3 Hz signal. So the high frequency signals, these are the high frequency signals in comparison to this, they actually started behaving like a low frequency signal after sampling or digitization. Fine. This process is called aliasing. This process is called alias. Alias, you know the meaning. Usually it is used, মানে যেটাকে বাংলায় বলে না ছদ্মবেশে বা ছদ্মনাম kind of. So that means it is actually it used in the context of in the criminal language mainly because you probably heard or you read in the newspapers or channels that the so and so terrorist alias actually a terrorist alias is so and so name or like that. So it is, but obviously the idea is here that the high frequency signals, they actually behaving or they acting like, okay, that means suppose they are kind of, though they are not the low frequency signal, but they are behaving like a low frequency signal. Okay, so but anyway, high frequency signals are not criminal, of course, but they pose as if they are the low frequency signal. So that is the thing, and that means what happens? That means you cannot recover from here. You cannot get back this signal when you will again convert it. So you cannot get back this signal. So that is the problem. That is the danger associated with this. So you cannot go back here also. From you cannot go back. It's not possible. So that means some distortion occurred. This is why it is happening, because the signal got distorted. It should convey a message, but it is conveying different message. So it got distorted. So that is why this distortion is called the aliasing distortion. And it's a very famous term used, and on this you will learn details in your advanced courses also. Fine. Now, is it okay to everyone?
So could
Yes,
you
sir.
explain
Okay,
this again, sir? Like the aliasing part, like
অ্যালিয়াসিং কোন স্পেসিফিক পার্টটা বলছো বলো, মানে কোনখান থেকে এক্সপ্লেনটা করবো আমি বলো।
মানে স্যার আমার যখন 0.6 মানে যেটা আমার cos 6 পাই যে আমার যে সিগন্যালটা
হ্যাঁ,
যেটার ফ্রিকোয়েন্সি 3 ইয়ার্স,
হ্যাঁ,
ওটা যখন আমি আবার ওটাকে অরিজিনাল ফর্মে নিয়ে যাব তখন তো আমি
হ্যাঁ।
ওটা এক্স্যাক্টলি পাবো, কেন ওটার
ওটা তো
মধ্যে আমার
এক্স্যাক্টলি
কোনো
পাচ্ছ, ওখানে
ডিস্টরশন
কোনো ডিস্টরশন হয়নি, এক্স্যাক্টলি
হ্যাঁ,
এক্স্যাক্টলি।
বাট 14 পাইটি আর 26 পাইটিটা জাস্ট বিকজ আমি ওটাকে ওর আমার নাইকুইস্ট মানে এই ক্রাইটেরিয়াটাও ফুলফিল করছে না,
এক্স্যাক্টলি
তার জন্য আমি জিনিসটা একটা ডিস্টরশন পাচ্ছি।
ডিস্টরশনটা পাচ্ছ, বিকজ দ্য ডিস্টরশন, হোয়াই ইট ইজ ডিস্টর্টেড, ইট ইজ ক্লিয়ার ফ্রম দিস এক্সপ্রেশন, না?
কেন কি আমি
Okay.
আবার ওটা 0.6 পাই
Exactly, 0.6.
পাই
So as if this signal coming from this, but that is not the case. This is actually coming from here. Similarly, this signal also seems to be coming from here. That's after sampling it's coming. No, it is not true. This is actually coming from here after sampling. So that means what? These signals got distorted. So the information or the shape it should retain is not, it cannot retain. Or the information it is supposed to convey cannot convey or cannot give. Getting the point? So that is why it is distorted. So this distortion is called aliasing distortion.
and the whole process is called aliasing
Aliasing, exactly. Aliasing, হ্যাঁ, যেটা বলে ওই বললাম না যে বাংলায় বলে ছদ্মবেশ বা ছদ্মনাম যেটাকে বলে, ওই মানে এরা as if এর মতো বিহেভ করছে বা এর ছদ্মনাম নিয়ে, হ্যাঁ, বা শেপ নিয়ে, রূপ নিয়ে, যে বাংলায় বলো যাইভাবে রূপ নিয়ে কাজ করছে, হ্যাঁ, সেই জন্য এটাকে aliasing বলে। It's very interesting. Okay. Okay, now the point is, এটা তো বুঝলাম আমরা যে what is aliasing, the distortion is called aliasing distortion, all this stuff. It's okay. But the point is now what is the way to restrict this kind of aliasing distortion? What is the possible solution? Obviously you can understand the possible solution is you have to ensure that you should obey the Nyquist criterion or that relation written over there. You have to obey. That means here the quantity, the omega 0, actually the problem is if it is less than or equals to pi, if it exceeds pi, okay, exceeds pi means just you look at the second and the third case, it is 1.4 pi after sampling, and that is 2.6 pi. Okay, so if it exceeds, so we have to basically restrict that omega within pi or at least equals to pi maximum. If it exceeds the pi, as in the second and the third cases, so that is a problem. Then there will be problem. But if omega 0 less than pi, then there will be no problem. Okay. Suppose for example, if you take this example, a value, suppose instead of 0.1 second interval, if you just replace it, and if you take suppose 0.02 second, if you take this sampling interval or sampling period, then what would be the value of fs instead of 10 hertz? Anyone please tell me? Very good. 50 hertz. 50 hertz. So 50 hertz. Now if you go for sampling with this 50 hertz signal, then this signal, first signal could be written, এটা কিভাবে লিখবে, cos ব্র্যাকেটে কি হবে আর্গুমেন্টে, কেউ একটু বলো তাড়াতাড়ি চটপট, কত হচ্ছে 0.12 পাই n, এখানে এই কেসটা কি হবে, সেকেন্ডটা cos
0.28
very good 0.28 পাই n, আর এটা ক্ষেত্রে কি হবে cos
0.52
very good 0.52 pi n. So দেখো এবার if you just carefully note the arguments, এটা cos arguments গুলো দেখো, so in all cases or for each of the omega 0, if you look into carefully, are all less than pi, so then they are distinct. ঠিক আছে, এটাই কিন্তু tricks. Then they are distinct, then there is no problem. So they can retain their original frequency or the spectra. They can retain that. There is no problem. And the original shape as well. So there will be no distortion. Now in this context, if I ask you, what is the lowest sampling frequency? In this case, in this particular example, actually, this case means which the lowest sampling frequency. কতটা মিনিমাম, কতটা নিচে আমরা নামতে পারবো স্যাম্পলিং ফ্রিকোয়েন্সি, যাতে করে তিনটাকেই ডিস্টিংক্টলি এক্সপ্রেস করা যায়? কে বলবে ইন দিস পার্টিকুলার কনটেক্সট?
13.
হ্যাঁ
13.
13 কি
13 hertz.
ভেবে বলো।
26 hertz.
26 hertz.
26 hertz. Sorry.
Very good. 26 hertz. Okay. 26 hertz. Very good. So this is essentially what happens if anyone violates the sampling criterion or doesn't follow the sampling theorem. Okay. So I have tried to illustrate the fact with a very, very simple example of what could happen, what could be a possible outcome if this is violated. Okay. If it means if the sampling frequency is not adequate, or adequate means it is not at least twice the highest frequency component. দুটাকে দিকে নিয়ে আসলে সুবিধা হবে তোমাদের, হয়তো মানে এইভাবে অনেকে বলে, সেম থিং যদিও এই, ঠিক আছে, মানে যেটা বলতে চাইছি, যদি এটা তোমার যে হাইয়েস্ট কন্টেন্ট বা সিগন্যাল ফ্রিকোয়েন্সি যে আছে, এটাকে অনেকে এফএমও বলে, যার জন্য দেখবে ম্যাক্সিমাম ফ্রিকোয়েন্সি অফ দ্য সিগন্যাল। এনিওয়ে, সো আমাদের এখানে যেহেতু কস আছে এবং এখানে একটাই সিগন্যাল আছে ফ্রিকোয়েন্সি, তো আমাদের এটা খুব একটা ম্যাটার করে না। সো টোয়াইস এম দ্য হাইয়েস্ট সিগন্যাল কন্টেন্ট বা সিগন্যাল ফ্রিকোয়েন্সি কন্টেন্ট যেটা থাকবে তার টোয়াইস, তার থেকে এটা ছোট হতে, বড় হতে হবে স্যাম্পলিং ফ্রিকোয়েন্সিটাকে, অর অ্যাট লিস্ট মিনিমাম টোয়াইস হতে হবে, তার নিচে তুমি যেতে পারবে না। দেন দেয়ার উইল বি aliasing distortion and the message, তারপরে বুঝতেই পারছো যে মেসেজটা আমি কনভে করতে যে কনভেট হবে না, মানে মেসেজটা ডিস্টর্টেড হয়ে গেল। and there is no way, এবারবার যে কথাটা বলি, there is no way you can recover the original signal on this earth. There is no way till date that you can recover. So aliasing distortion is a very dangerous thing. তোমরা যখন কমিউনিকেশন পড়বে না, দেখবে ডিটেইলসে পড়বে, মানে এর পরবর্তী যে কোর্সগুলো আছে অ্যাডভান্স বেসড অন দিস, ডিফারেন্ট টাইপস অফ কমিউনিকেশনস এন্ড প্রসেসিং সিগন্যালস, ইমেজ প্রসেস, everywhere you will get this stuff and in rigorous analysis চলবে, মানে এটা এখন চলতে থাকলো তোমাদের সারা জীবন অ্যাকচুয়ালি। ওকে, ঠিক আছে, আপাতত এটা আমি ক্লিয়ার করলাম। নাও এবারে ধরো এক মিনিট, নেক্সট স্লাইডটা কি ছিল? ওকে, সাপোজ, আচ্ছা দেখতে, এই স্ক্রিনে দেখতে পাচ্ছ এই স্লাইডটা যেটা খোলা আছে? ওকে, ফাইন। আচ্ছা দেখো, সাপোজ তোমরা জানো অলরেডি যে ডিফারেন্ট ডিজিটাল সিস্টেম, ওকে, ডিজিটাল সিস্টেমস অ্যাকচুয়ালি যারা ডিজিটাল সিগন্যালের উপর কাজ করে, বিভিন্ন রকমের ক্যালকুলেশন করে, প্রসেসিং করে, যেটা আমি বলছিলাম একটু আগে, এবং প্রিভিয়াস স্যাম্পলস নিচ্ছে, নতুন মানে ইনপুটে নিচ্ছে, নতুন স্যাম্পল প্রডিউস করছে, আউটপুটে প্রডিউস করছে, এবং যেটা বললাম মাচ মোর ডিজায়ার্ড ফর্ম অর ইন এ বেটার ফর্ম লাইক দ্যাট। সো ইন জেনারেল ট্রেডিং, একটা যদি তোমার এরকম সিস্টেম থাকে, একটা ব্লক যেটা একটু দেখলাম, তার ভেতরে অনেক কিছু হতে পারে, ডিফারেন্ট অ্যাক্টিভিটিস মে গো অন। সো ইনপুট ফিড করছো, আউটপুট তুমি ওখানে পাচ্ছ, বোথ আর সিগন্যাল, বোথ আর ডিজিটাল, ইন ডিজিটাল ফর্ম। ওকে, নাও এবারে ধরো আমি কিছু যদি এক্সাম্পল নিই, কিছু টিপিক্যাল মানে সাবসিস্টেমই বলতে পারি বা মানে বিভিন্ন কম্পোনেন্টস বলতে পারি, সেগুলো নিয়ে যদি আমি একটু একটু ডিল করি, যেটা আমাদের ডে টু ডে লাইফে এইরকম ধরনের ডিজিটাল সিস্টেমকে বা ডাইনামিক সিস্টেমকে রিপ্রেজেন্ট করার জন্য আমাদের কাছে অত্যন্ত ইম্পর্টেন্ট। তো সেরকম কিছু এক্সাম্পল হচ্ছে, ধরো ফার্স্ট এক্সাম্পলটা আমি নিচ্ছি, তুমি বুঝতেই পারছো এক্সপ্রেশন দেখে, এক নম্বর এক্সপ্রেশন দেখে, বেসিক্যালি ইটস অ্যান এক্সাম্পল অফ অ্যাকুমুলেটর। সো what does an accumulator, does an accumulator actually do? So accumulator simply, you know, that it simply adds up signals or sequences, because I'm talking about the digital case or discrete time case. So the sequence, there are different sequences, different samples. So it basically keeps on adding. Now from the first expression, you just see it yn equals to, carefully look at the expression, yn equals to summation L starting from -infinity to n x of n. This is the first expression or first equation. this actually adds up, adding up from infinity, minus infinity, and this is adds up to the present instant n. This n here is actually the upper limit. Look at this upper limit. The n is here actually the present instant. Whatever the present instant. Suppose at this moment it is suppose 10:30. Suppose or 10:40. So this is the present instant. After 5 minutes it will be 10:45. Then that will be the present instant at that point. So at that particular instant, whatever sample you are getting, it is the present sample, and you are just adding. So it's keep on adding and adding and adding. Okay. Now, suppose if another signal comes, as I mentioned, in the immediate next instant, another sample means x of n plus 1. You know, xn. The next sample is xn plus 1. The next to next is xn plus 2. Or immediate, they're coming after x of n. So the sample just came just before x of n, that is xn minus 1, you know that. So similarly, if it adds up to xn, that means that is the present instant, up to the present instant n, so that is xn. So the immediate next instant is the sample, that is xn plus 1 comes. It will also adds it up. Okay, now again, so this addition is kind of, you know, what happens in your computer, actually in an accumulator. Why I have used the term accumulator? So it's a simple, maybe simple adder I can use, but again, it's a technical name is, I suppose, the accumulator in the context of computer. People use it. So accumulator in this, actually they keep on adding and they accumulate. So any new number or any new, in this case, the sample comes, whenever comes, it basically adds it. What already exists, that means the previously, what number already exists, that number comes from the already all the previous summations. Okay, so after summing up to n, whatever number it will get, it will basically store it or keep it within the accumulator. So immediate next number or the sample whenever comes, that is xn plus 1, it will just add these two numbers, and again this will be accumulated. And if the next to next sample when come, that is xn plus 2, again whatever accumulated value is, it will just add with that and keep it or store it. This is the concept. Okay, now the first expression can be written in different ways, many different ways. Now, one of the possible ways could be the expression number 2. Just to see here, what I have done, I basically divided into two parts. Look at this. Starting from minus infinity up to n minus 1, that in the immediate previous instant, I happen to write n. N is the present, just present instant, just immediate past instant. So n minus 1, I have written up to that, and xn I have separated, kept separate. So look at this. This clearly indicates up to this one. This first term indicates whatever have been added till the past instant, immediate past. This is indicating the present instant. All the past instances have been added over here. Okay, this is the present instant. So that means this can be written as y of n minus 1. If this is written as y of n, okay, then obviously this can be written as, because the upper limit is n minus 1, so it will be n minus 1, y of n minus 1. That means up to n minus 1th sample I have added. It's y of n minus 1. Done. Past. Encompassing all the past samples, or taking care of all the past samples. So done. This is the immediate present input. But just have come rather at this instant. So xn. Now you are adding. So this is another way to represent. Look, this expression actually comes from here. But there is a beautiful, outcome of this kind of representation. So actually, the accumulator can be described. You just see, this is actually the difference equation. You have yn minus 1. Okay, so this accumulator, the same accumulator, which was previously described by here, this expression, this is actually described by this expression also. So accumulator is described by this difference equation like this. So what we have done? So what is the difference between these two types of expressions? So basically, with this we have tried to avoid these infinite summations. We have tried to avoid that of equation 1. Rather, what we have done, we have tried to express in terms of the finite quantities. This difference equation I'm talking about. Okay, but this expression or this equation is what you know that it is called the recursive equation. Recursion. Why? Because it requires recursion. You know, the recursion is actually feedback. What in software you call recursion is in hardware is actually feedback. It's just a feedback. So go back to this expression, this representation. This is a feedback. So it is nothing but the recursion. Factorial, তোমরা C programming করেছো তো সবাই? So factorial calculate করে recursion করেছো, যেমন for example. So it is basically that recursion. Fine. So to compute the present output, we have to have the immediate past output. That is the recursion. That means bringing it back from the storage. That is actually the feedback. And then add up to the present sample, what you are doing now here in this case. So whenever there is a recursion, that means the feedback, there is a possibility of oscillation or instability. Please note it carefully. Whenever there is a feedback or recursion, there is a possibility of oscillation and instability. You know that quite well. In your circuit, you have already learned the oscillation, criterion for oscillation or instability. That is related to the feedback. But that feedback actually comes from the positive feedback. Negative feedback, no. So anyway, I'm not going into that. But for the time being, as far I am concerned with the representation or the style or the mode or the type of the representation. Now, on the other hand, if you compare this with that, as I mentioned, if you just look into this expression 1, this is actually non-recursive. There is no feedback. Look at this carefully. There is no feedback, nothing. So it does not require that the past output to be brought back like this. It is basically you are bringing it back. So this path is not required in realizing this expression or equation, though both of them actually representing the accumulation operation or accumulator. Okay, now again, this equation could also be represented like here. Yes, this one. This equation could also be represented like this. You just again see, again, yn equals to x of L minus infinity to n x of L. It's fine, no problem. Now what I'm doing, from here you just come here. So up to -1, I'm dividing it into two terms or two parts. The first term or first part actually dealing with all the negative arguments. Look at here, from minus infinity to -1. All the negative arguments, the negative values of L. But the next term or the second term actually dealing with from 0 to positive, all the positive arguments or values of L. So from 0 to n. Now, as usual, by the same logic, you can represent this first term as y of -1 because the upper limit, the maximum, the sample or the term it added, it x of -1. So obviously, at that point you got y of -1. So that is represented by y of -1. And rest of the things is written like this from L equals to 0 to n. Okay, so 0, you know that in your continuous time domain also, but t equals to 0, that indicates so what comes before that is kind of the initial. In your circuit theory also you learn that the initial condition. So that y of -1 is kind of behaving like or acting like an initial condition for this expression. So that is the initial condition, and all other things that is from L equals to 0 to n, whatever value of n it is, doesn't matter. So 0 onwards. Okay, 0 onwards. So all these are the means present and the future samples. All the samples that are coming or yet to come. So this second term is just representing this. That means suppose you have initiated a operation or you have just switched on your circuit or system. So at that point, that means switched on. So whenever it is on, you are switching it on. So switching is on means t equals to 0. Or here in this case it is 0. The first sample you are getting. Okay. So that means that is the present instant at that point. So from that you are computing. Okay, you are adding. So you are just keep on adding terms one by one. But before that, before you switch on, or before you just initiate it, whatever already stored there, whatever value you had already at that point, that actually indicates the initial condition. If this is 0, that means your initial condition is 0. Suppose a circuit having that capacitor or inductor, they actually store charges. Their capacitor stored charges, everything actually, and inductor store current. So this way you can say that if your circuit has elements like inductors or capacitor, then you can expect some kind of initial condition there. So before starting, or sorry, just after starting the circuit or switching on the circuit, you can expect some kind of behavior already, because already it stores or it retains some previous values in terms of current or charge or whatever. Okay, it actually. So this is something that this representation actually tells you something like that. Yeah. So this initial conditions, and then t equals to 0 onwards, or L equals to 0 onwards, what is happening. So L equals to 0 or N equals to 0 does actually the same thing here, as you can understand. So here what exists before N equals to 0, that is the initial condition, and that from that point onwards it keep on basically adding. Now the point I want to stress with these three types of expression of a single accumulator. So what I am trying to convey, the message is that depending on the how you are expressing, or the style of expression of equation of the system, of the same system, so you will basically also learn in future that the same system is characterized in a completely different manner depending on the expression. Depending on the expression or the style of expression, the same system could be defined as a linear or a non-linear. Okay, so it can be defined, or it can be modeled like that, depending on the expression or the representation, the same system. So that is why people call the system characteristics could become completely different depending on how one is going to represent the system. This is a very it's interesting thing. So this example actually tells you. Okay. So anyway, the next point is this thing, I think. No, before that I have to do another thing. Okay. Next, we can talk about একটু দেখে নি, আমার একটা স্লাইড ছিল মনে হচ্ছে। Yes, this one. Yes. Next, our topic is what is called upsampling and downsampling. You have already, this is another system or subsystem, another component, sampler. What is called the sampler? First we discussed about the accumulator, then what is called the sampler. Now in the upsampler, or the operation is called the sampling. That means upsampler is the upsampling. Now where is this upsampler used? Upsampler is used first, this expression represents what is upsampler. Now first let me discuss, then I am explaining the mathematical operation. So actually the upsampler is, or better to say, the upsampler is used when you want to change the rate of the sampling. As you can understand the name, from the name it's clear that upsampling, because after all you are increasing the rate of the sampling. So upsampling, suppose you have a 10 Hertz signal. Now suppose the requirement, depending on your application, the requirement is such that you have to upsample it, or change the sampling or the frequency from the 10 Hertz to 20 Hertz. Suppose. Now, this is a very commonly used operation. It is not very rare. It is a very commonly used. In many occasions, you will encounter this thing, upsampling. Similarly, there is the reverse operation is called the downsampling. You have a high frequency sampling done, suppose in a higher frequency, and the application or specific area demand that you have to lower the frequency, downsampling. Okay, just a reverse process. But the mathematical expressions and operations in details I'm going to discuss now. Now, if you look at the block diagram representation, the xn of xn, this is the block with a arrow pointing upward, L, and xn you are feeding to this box and you are getting yn. Now, what is xn? Xn is actually your input. So you can understand whose sampling rate of sampling obviously low, suppose 10 Hz. Now with this I'm going to increase its sampling rate. So as I mentioned, in a much more better or desired form, I want to get the output. That is why this operation is done. So this is a system. This system is called the upsampler, and this is the representation of the upsampler. Now what actually mathematical operation is doing in this case for you? Yn is the output, that is equals to x of n by L, where n equals to 0 plus minus L plus minus 2 and so on and so forth, and 0 otherwise. What is the meaning of this? The meaning is this, it is very clear, please note, because all other discrete time of the digital signal, so argument can never be anything else other anything other than integer. So the argument has to be integer. In whatever form you represent, doesn't matter. As far as the discrete time or digital signals are concerned, their argument should always be an integer. You know that quite well. Okay. Now what happens? Actually, n by L has to be an integer. And the point is, how it could be possible? Possible because just see, if n is 0, it is 0. No problem. If n is 1, then it is 1 by L. What about the value of L? Doesn't matter. Suppose L has a value 3. Suppose. So what would happen? So 1 by L, obviously it is not an integer. So you cannot take this argument. You cannot take, that means you cannot take that sample. So x of 1, you cannot accept. Then suppose n equals to 2, x of 2. 2 by 3, again, not integer. So you cannot accept the second sample as well. Things from the perspective of the input. Then comes x of 3. X of 3 by 3 is 1. Okay, accepted. The argument is 1. So 1 by 1, 3 by 3 is 1. Accepted. So x, this, then it becomes actually your y of 1. So I'm sorry. It actually became x of 1. X of 1. So it is accepted because 3 by 3 becomes after all 1. So that is why it is written, look at this, it is basically the integer, n should be the integer multiple of L. Then only you will get the argument equals to an integer number, any integer value, it's possible. Otherwise, if this is not the case, then you have to put forcefully 0. That is the case. Now see, let's take an example. Suppose this is my xn. This is the xn. You are feeding it to this, and here L is 3. L is basically 3. So as you can understand, L actually indicates the sampling up, because it's the up sampling. That is why arrow is upward, up sampling. Similarly, for the down sampling, arrow is downward. That means it indicates it is basically decreasing the rate. It indicates it's increasing the rate, making it up, making it down. So that is why L is kind of actually gives you some idea that how fast or how much or at what rate it is actually increasing the sampling. Okay, so suppose xn, look at the green colored signal, xn, if you look at the samples, so for n equals to -1 you have -1, n equals to 0 you have 1, n equals to +1 you have 2. Now, if you feed this signal to this upsampler, whose sampling rate is related to this L, and that is equals to 3. Now, what we will do, as per this mathematical relation, suppose when the first sample will, suppose -1. For n equals to -1, if you put -1 within this expression, -1 divided by L is 3. So -1 divided by 3 is -1 by 3, which is actually your not an integer value. So that means it will give you 0. It will give you 0. Now it is look at this thing here. You are getting 0. Fine. For y of -1, it is getting 0. Now then what would happen? Then after that, n of 0. So n of 0 means what? 0 by 0. Sorry, 0 by 3. 0 by 3 is 0. No problem. So 0 by 3 is 0 means it is integer. So whatever value this sample has will exactly come and sit at this 0 value, 0 position. Fine. Similarly, when you have the value, suppose then n equals to suppose here n equals to suppose 0, after that 0 plus 1. So when it is plus 1, what would happen? Plus 1 divided by L. 1 divided by L is 3. So it is 1/3 plus 1/3. So plus 1/3 is not integer. So that means you have to add 0. So it is 0. Similarly, when after n equals to 1, it will be 2. So again plus 2/3. 2/3 means not integer, 0. So 0 is added. Now again n equals to 3. So 3 means 3 by 3 is 1. So that is x of 1. So x of 1. So what is the value of x of 1? X of 1 is 2. So 2 comes directly here. So in this fashion, in this manner, you just see actually you got a upsample version of the signal yn, and this is the upsample version of the xn. And in between two consecutive samples, here you have added or padded 2 zeros. And the general formula is whatever the value of L, you have to add 1 means L minus 1 number of zeros in between two consecutive samples. Just to see, just to compare these two signals. Between these two samples, there are 2 zeros padded. L is 3, so 3 minus 1, 2 zeros. Okay, similarly between these two samples, there are 3 minus 1, that is 2. 2 zeros have been padded. Look at this. So if you compare this as if this signal is kind of the stretched, no? In a stretched kind of, it is you are kind of holding this to a someone has stretched it. So this is the upsample version. Yn is the upsample version of xn in this context when L is 3. Now you can play with different values of L. L is 1, L is 2, L is 4, 5 different values, and just to see how the shape of the signal actually changes. Okay, so with this typical example, I have tried to show you exactly what happens during the upsampling process. And the representation you should note carefully, this upsampling representation of the upsampler or upsampling operation. Okay, so like that. Anyway, later on we will also see that this upsampler actually it is not a time invariant system, rather it's a time varying system. We'll see that later also. But anyway, if you apply the same concept, if you understand upsampler, if you apply the same concept for your downsampler, that is the picture given in the bottom panel. So there xn, you are fading to the box, right? There's an arrow pointing downward. M again indicates the factor, the downsampling the factor, or related to the rate of the downsampling. Now, in a similar manner, you can think that whatever signal you are getting, that signal, if it is extended in the time domain or in the n domain, in along n axis rather. I should not say domain. In axis, then of course this will be contracted. That means some of the samples you have to basically ignore. And how to ignore? There should be a rule. There should be a protocol, and that is the rule. Rule is that you are expressing yn equals to x of m into n. M is this factor. Okay, this factor. Here L was this factor, upsampling factor, it's a downsampling factor. M is this factor. Now this expression indicates what? This is true for n equals to 0, plus minus 1, plus minus 2, and so on and so forth. And it is 0. Actually, this you don't need to write this 0 otherwise, because this is an additional redundant information, because you just see that there is no concept of any 0 adding as far as the as far as the downsampling operation is concerned. Unlike the case of the upsampling. In the upsampling case, between two consecutive samples of xn, we have to add or pad zeros depending on the number, depending on the value of the this L. Okay, but here you don't need to pad. Rather, you are not adding any new sample. Rather, you are rejecting some of the samples. And how you are rejecting? Just based on this formula. If you just have, suppose when your n is 0, suppose n is 0. When n is 0, then x of m into 0 is 0, so x of 0. So here also when 0, this 0th sample comes directly to here at 0. Now suppose when n is 1, when 1, because m has a value of 2, so 2 into 1 is 2. So x of 2 will come at n equals to 1. So x of 2, what is the x of 2? Here, this one, 3. Look at it comes. So in between this and this, I am ignoring this. Fine. Similarly, when n equals to 2, 2 into 2, m is already 2. So 2 into 2 is 4. So the 4 means this sample will come here for n equals to 2. So in between this and this, I'm ignoring this. Likewise, the same story is applicable for the negative side. So ultimately, you just see this kind of contracted, as if you are pushed from this two direction, become or squeezed. Okay, here as if it is expanded, here it is as if squeezed. So this is the two different types of operation. But again, as I mentioned, that both are extremely important, and in many occasions you will encounter these things and you have to apply these operations, and both of them actually time varying system. This actually that is why it doesn't directly come under the LTI system analysis, but anyway it is important. That is why I am mentioning in this particular context. Fine. Okay, now suppose with this, okay, now I can move here for this slide. Yes, this one. Rather, just a minute, let me open it, paint, then it will be okay. Okay, this system is what is called the M point moving average system. Please note it carefully. It is called M point moving. M may have any value. M may have any value. Now the description is of this type of system is that this is Yn. So Yn is taken as the average of the present value and the past. Please note m minus 1 values. If you carefully look into the expression or follow the expression, please note when k equals to 0, this is x of n. Please note when it is k equals to 1, it is x of n minus 1. That means immediate past value. When k equals to 2, it is n minus 2. Past, again it's another past sample, n minus 3, another past, and this one. That means in total, actually total there is m number of samples. Please note. And that is why you are dividing by m. From 0 to m minus 1 means m number of samples. So m numbers of samples are being added, and then it is divided by m. So that is kind of average. Fine. But if you carefully follow the addition, it is actually the present k equals to 0 indicates the present, and all other values indicate the past samples. How many numbers of past samples? M minus 1 number of past samples. So that is why I mentioned that the present value and the past M minus 1 values are being added and then averaged over the total number. Of course, it is an accumulator in the sense that the first it sums up because if you just ignore this part for the time being, so it is nothing but the summer, adder, accumulator. So the first operation it adds up, it sums up, and then the accumulation is over all this number of samples, okay, and after that it actually divide by n. So that is why it is an average. So as I mentioned, the present sample and the past M minus 1 samples. It first adds, then it averages over these total M number of samples. And that is why it is called the average system. Please note, that is why it is called the average system. But I have mentioned that it is not only the average system, rather it is and why it is M point moving average system. What is M point? Because total number is M. That is why it's M. M may have any number. Okay. So, but the point is, the question is why it is called moving. Why it's called moving. That is the point to ask. Average is okay. We got it. M point is okay. Got it. But why it is moving? Moving average system. That is very interesting. Okay. Let me try to describe it in just a minute. Let's see whether I can do it or not. Okay. Yes, it is moving. Suppose this is your window. This window, probably you can see the sliding of the window from one end to another. Everyone can see it?
Yes, sir.
Fine. Now suppose this is a particular pattern or samples or sequence of samples is given. You have to make this or apply this M point moving average operation on these samples. Now you just see, first follow the expression very well. Suppose here M is equals to 1, 2, 3, 4, 5. Got it? These 5 samples. Any number of 5 samples. Any 5 samples. So first I am adding these 5 samples. Okay. So I'm first adding these 5 samples. What is there hidden by this window? Now, just a minute. Let me resize it a bit. Now I think it is okay. It is better. Yes. So what is there within this window? I am just adding all these 5 samples. Fine. Now I am sliding this. What happens? Now, number of samples that will come or that will be covered by this window or that will come under this window will be added and averaged over. Now just see, with this sliding of window, initially these 5 samples were being added first. Now whenever I have slided it, one sample in the right hand side, what happens? In this case also it is adding and averaging over the 5 samples, but this samples comes out of the window or goes out of the window, and another new sample, that is n equals to 1, comes within the window. Can you visualize the thing? Next, on the next operation, I will again slide it one sample in the right hand direction. So what happens? This samples again goes out of the window, and another new sample, that is for n equals to 2. Just look at how the sample is entering within the window. It enters within the window. Got it? Similarly, if I move further, then again I am leaving one sample in the left hand side and I am adding another samples, that is n equals to 3. So in total, always within the window, I have 5 samples to be added and averaged over. But with each movement, that is what is moving, because it's a dynamic thing. It is always changing. So some new samples are being added while other is actually rejected. So that is the average thing is actually always changing. Averaging over all the things are always changing. This is the philosophy. Got the philosophy of the operation?
Yes, sir. Yes, sir.
Okay, fine.
Yes, sir. Yes,
Fantastic.
sir.
Okay, so this is all about. That is why it is called the moving, because this average is not fixed or constant. This is always being moved, always being changed, or actually is changing. Okay, always is changing, like this. It is basically moving. Okay, always it for this case, number of samples is m in general. So m number of samples that is coming within the window will be added and then averaged over. That's all. So with each operation or each step, it moves further and taking one new sample and rejecting on one old sample. This way the operation actually goes on. Anyway, that is why it's called the moving. Now, this operation is very useful in the sense that, suppose, in noise elimination or data smoothing, you have to smooth the data. Okay, there is some arbitrary or sudden variations, especially that occurs with the noise. So there is some sudden change, unwanted changes occurs. Now, in your signal or in your data, you want to make this thing smooth a bit. So for data smoothing or noise elimination purpose, this operation is very useful in the sense that, suppose you have a signal is xn, this xn, which has suppose 2 parts. Now, any signal when you want to transmit to any channel, whether that channel is your guided channel or is wired or wireless kind of, so whatever the medium is, always there would be some sources of noises, maybe impaired by the noise. Sometimes the noise disturbance is more, sometimes it's less, but there is some noise, always some disturbance. So that's what I mentioned, that actually disturb the pattern or the shape of your signal. So that means it sudden rise, sudden fall, something like that. So sometimes some glitches occurs. Okay. So anyway, the purpose is we have to smooth or we have to eliminate those things as much as possible. That is our target, so that we can get back our original signal, or we can retain the shape of the original signal. Now, if you divide the signal has a 2 part, xn, this signal. This is basically a noisy signal. So if you divide it into 2 parts, one part is associated with the true signal. This part is associated with the true signal. This part is associated with the true signal. This is a true signal, and this is indicating you some kind of noise, as I mentioned, due to any kind of disturbance. Okay, any kind of reason, disturbance or unwanted things like that. So noise. So basically here the noise is actually additive in nature. So in mathematically you can eliminate this noise and the signal. Suppose, for example, if you have a smooth time varying sinusoidal signal, suppose, and noise, sometimes the noise came and make this kind of spark ups and down here. So what would happen? The resultant signal will look like this. Now I can actually, this is suppose a noisy signal. Now this could be represented as this smooth signal plus this noises. So this is written over here like this. So it is basically the additive noise. Okay, so noise is actually added with the signal. So sometimes it is making the amplitude more than its actual value, or sometimes it is making it less than its actual value. So it's a sudden disturbance, sudden occurrence. Okay, ups, down, like that. So it's something like that. But it is how it will happen, when it will happen, nobody knows. It's completely an unpredictable manner. It's a random thing. So anyway, whatever it is, so this is kind of, so but our objective is we want to smooth it. We want to smooth it or get rid of the effect of this noise as much as possible. Now, what to take if we apply this moving average system, or if you pass this signal, noisy signal, through this moving average system. Now you just see, as mathematically these two things could be separated. Then what happens if you apply this operation on the signal? It doesn't matter. Okay, it doesn't matter, no problem. In the original signal, noiseless signal, noise-free signal. But the noisy components, as far as the noisy components is concerned, these components, if you increase this number of samples, if you average over a large sample, and what happens that actually these components diminishes, and in usual process where the number of samples is very large, the average of dn would be almost equals to 0, because after all it is noise, it has no particular shape. Sometimes very high positive value, sometimes very high negative value. It's like that. So, and if you actually add it, then there will be some cancellation. But again, if you add it and average it over a very large number, so almost you can understand that denominator is very large. So it will give you almost a 0 value. And that is the beauty of the moving average system. Okay. So you can say the moving average system, sometimes in many applications in future, you will see that it is actually called the data smoothing system also. Okay. And in different experiments also, you will observe this thing. This is just in philosophy I'm sharing with you, but in practice, you will do it in our department. You will do it in some classes. Okay. In the future, you will do it. So how to smooth it, how to tune all these kinds of things to increase the impact of noise, and then how these things are getting impacted, what a number of samples you should take. There are some mathematics also involved. So there are some rigorous procedures and treatments are there, and experimental things are also there. So you will get exposed on all those things in the future. Okay, just to remember that this is the system, and this is the operation or the principle of operation, and this is one particular application. Okay, just okay. Now, okay. Now, in different digital systems, as far as the classifications of the different systems are concerned, the systems are linear, the systems are non-linear. You know that quite well, how to define the linear system and non-linear system, because you know that one have to be, as far as the linear system is concerned, that system should follow two principles, obey two principles. One is that homogeneity, and another is the superposition. So what is homogeneity and what is superposition? I think everybody knows that, because already in the examination, this type of question you have already encountered. So you already know it quite well. But the point I want to mention is that your homogeneity and superposition, that whenever you will test whether any signal is linear or not, whether any system is linear or not, whenever you will test, the first thing that you have to apply is called the homogeneity. Homogeneity means, if you multiply with some particular value input, the output is going to be multiplied by the same value. So that means if you multiply in signal xn by alpha, the output yn will also be multiplied by the alpha. And a corollary of this homogeneity is that, or this principle is that if the alpha is 0, then obviously if the alpha is 0, that means your input is 0, alpha into xn, so your input becomes 0. If your input is 0, output is 0. That means 0 input should provide 0 output. Please note, 0 input should provide 0 output. That is the corollary of the principle of homogeneity. Superposition also tells you that if you have two or more than two inputs, suppose alpha x1n, beta x2n, etc., and if your output should also be a superposition of the individual outputs. That means if x1n provides y1n, then alpha x1n will provide alpha y1n, and beta x2n provide beta y2n, then your output will be the alpha x y1n plus beta y2n. And so on. There may be more than 2 also. So these two things, a linear system, if the system is linear, you know that system has to obey both of them. It is not that it obeys one and doesn't obey the other. Then it will not be defined as a linear system. So if a system has to be linear, it has to obey both of the principles, homogeneity and superposition. So first you will check, the testing method is, first you have to check whether that homogeneity principle is held or not. If the homogeneity principle is violated, then there is no need to further proceed for checking the superposition. There is no need. So then and there you can say this is not a linear system. But if the homogeneity principle is obeyed, if test is test result shows that yes, it obeys, then you should, but means test is positive actually. So then you should move further. You should proceed further with the superposition. If the superposition is also whole, then it's okay. You can confirm that yes, this is the linear system. Like that. Suppose for example, again the example of accumulator, you say you take yn equals to your summation L equals to minus infinity to infinity, suppose I am defining it like this. Okay, now this is a linear system, because you just test it. If you put x1 and x2, obviously when all the x's are 0, yn equals to 0. There is no problem on it. Now if you take x1n, if you take x2n and find a y1n, y2n, and again multiply by alpha, beta, and all those stuffs you do, then also you can follow that yes, superposition will be whole. So it is actually a linear system, but the same system can be written. You can write like this. The same system can be written like y of n equals to, suppose, y of minus 1. Following the procedure I've already discussed, y of minus 1 summation, it is minus 1, so the limits should start from 0. So all the positive values of the 0, say up to infinity, suppose. Now if you have problem with the infinity, you can replace it with the n, doesn't matter. So I'm just talking about the concept. Okay, so this is not a linear system. No? This system is, this representation, as I mentioned just a few minutes ago, that depending on the style or mode of the representation of the expression, actually the system characteristics of behavior changes. It's a very funny thing, but it's true. So look at this. The second representation, actually, though this comes from here, I've derived this from this expression, but this representation tells you that this is not a linear system, or you cannot ensure 100% whether it's a linear system or not, because making all the XL zeros doesn't guarantee that yn will be 0 because of the presence of this term. Getting the point? So who guarantees that this all the 0 values of XLs will give you the 0 value of, or will make yn equals to 0? There is no guarantee. There is no certainty that it cannot be ensured from this expression. But from this expression, it could be ensured. If all the XLs are 0, this is bound to become 0. Has to be. So that is why, because of the presence of this initial condition, that is y of minus 1 here, so you cannot say it is a linear system. See, so in this characterization of the system, y of minus 1, this second expression actually plays the role of that initial condition. So obviously system with the initial values, in a circuit theory you have again learned that if you have a capacitor with the charge storage, the inductor with the current, so these systems cannot be defined as an the linear system. So nonlinear system shall become linear if the initial condition is 0, precisely equals to 0. Now, if you guarantee that this is 0, if you ensure that this is 0, then it is okay. Then you can say it is a linear system. Okay. Now, we can test it. We can, though we know, but we want to test the system by some rigorous means. That is the usual procedure what we had actually. Suppose for example, suppose we have to take this example, means the procedure what we apply, that alpha x1 beta, two different inputs I have to take, okay, multiplied by the different constant alpha, beta, etc. Suppose first let me clear the screen. Suppose x3, which is equals to suppose alpha x1 plus beta x2. This leads to, okay, it is x3. So let me write it y3 minus 1 as per the previous expression. Okay, I'm trying to write. কি ছিল ফার্স্ট টার্মটা -1, সেকেন্ড টার্মটা কি ছিল জানো, প্লাস l equals to 0, তাই তো, l equals to 0 to infinity. Okay, and what would happen there? The summation was xl over xl. So xl means here you can understand what is the input. So input is basically of this form. Probably you have understood. X3 means actually this. So here I can write it like your alpha x1 l plus beta x2 l. This thing, this is I'm supposed to get. This should lead to this. Okay. Now, sorry, this actually leads to this. This input leads to this as per the expression of the behavior of the system. Now, on the other hand, if you comes from the output end or output side, or from the perspective of the output, if you look into it, so alpha y1, it is x1, the corresponding output will be alpha y1 plus here it is beta x2 will lead you beta y2. If you add these two, then how can you can write this? There it is actually for y1 means alpha, it is the initial condition first, and let's write the initial condition for it also. So that means beta y2 minus 1, this the two initial conditions from individual terms, plus and then summation over suppose l equals to 0 to infinity alpha x1 l plus beta x2 l. This thing. So this and this comes together, and this actually comes together. So these are the rearranged term. I've written like that. Now, and these two are not necessarily equal. Please note that I represent these two, this one and this one, are not necessarily equal, because just you see, when these two will be equal, only when this y3 of -1 would be exactly equal to this. So it is not guaranteed that this y3 of -1 will be exactly equals to alpha y1 of -1 plus beta y2 of -1, because the initial conditions can be set arbitrarily. But so that is why this test, this actually the superposition based test. So this clearly indicates that this system linearity condition cannot be held for this. It's not actually the linear system. But superposition condition or principle is not whole, so it is not a linear system. But again, as I mentioned previously, the means homogeneity principle was good enough. I have just done it, or just to show you the method how to rigorously one can test by applying the superposition also. But anyway, that xn equals to 0 doesn't lead to yn equals to 0 was good enough as far as this particular example is concerned. Now, in this context, let me share one or two very useful examples. Suppose if we have a system, if we have a system yn, which is the system is described by this difference equation. The difference equation is like, suppose yn equals to m xn plus c. Okay, this difference equation describes the input-output relation of a system, or a system is characterized and described by this difference equation. Suppose now it is a equation of a straight line. Probably you can recognize a very famous, very well-known equation. So it's a linear equation. It is an equation. It is an equation of a straight line. So it's a linear equation. Please note it carefully. Y equal to mx plus c is a very famous form. So it is, but if anyone asks you whether the system represented by this expression or equation is a linear, no, not guaranteed. It is not linear in the sense that if you make, this is your input, no? So if you make your input 0, then there is no guarantee that yn will be 0. It actually, in that sense, equation doesn't describe a linear digital system, because there is an initial condition like thing, that is C. See, only when C is precisely 0, I can say it's a linear system, but there is no guarantee from this expression. So you cannot say it's a linear system. So that means, as I mentioned, that even your initially charged capacitor or inductor with the initial flux is actually a nonlinear system. If, please carefully follow the statement what I'm trying to make. The initially charged capacitor, if the capacitor is initially charged, it is not, I'm not saying if a system has a capacitor, it is nonlinear. Only when the capacitor is charged initially, I mean, before you apply the switch or before you switch it on, if the capacitor has a charge. Similarly, if the inductor is stored as a flux, that means if it stores current, then only you can say that your system is nonlinear. But it is not like, I'm not trying to say that if a system has an inductor or a capacitor or both, then automatically the system will become nonlinear. So if the inductor doesn't have the flux, initial flux, or the capacitor doesn't have the charge stored there before the operation you start, then obviously it is not linear. So then the question of initial condition will not come. That is the thing. Now, anyway, that's a very nice example. It is sometimes in different interview, it is asked that cites an example that where this equation or the expression tells you it's a linear equation or linear expression, but the system that is obeyed by or obeys this equation or characterized by the equation is not a linear system. This is an example. This is the example of the expression. Okay. Now, another example. Suppose I think I have already mentioned in one of my classes, that is, let me remember it. Yes, I mentioned. That is, I've told you that if any signal is multiplied by another signal, suppose xn is multiplied by, suppose x1n is multiplied by x2n, suppose. This is a signal multiplication. Probably you can remember, not a scalar multiplication. And this signal, one signal or one sequence or one samples actually, sequence and another sequence, a set of samples, another set of samples, actually multiplied. and it will be, that you have to, the corresponding samples will be multiplied. Probably you can remember these statements. So they will multiply. So this multiplication, I think I have already discussed that this is not a linear operation. This is a non-linear operation. So non-linear, and the system, this multiplier is a non-linear system. Okay. So now suppose I am just for your simplicity, I am just writing x of n, an equation or expression which describes the this kind of system. Okay, this expression yn equals to x of n minus 1 into x of n plus 1. Now you have to prove mathematically, that means by rigorous method, that this is a nonlinear system. Nonlinear system. Now, if you look into the expression, what it does actually, this is the current instant of the input, output, present instant, y of n. And this is the past instant of the input, and this is the immediate future instant of the input. So immediate past value, the past sample of the input and future sample of the input is being multiplied, and you are getting the present value of the output. So this is the operation which is done or expressed through this equation or expression. So it is simply, if you see this, it is basically the multiplication of two different, samples. So it is basically this operation, this in general, signal multiplied with another signal. So this kind of thing. Now you have to prove rigorously through mathematics that this is a nonlinear system. The system that is characterized by this equation or expression is not a linear system. Now, one point to note: if all your xn's are zero, that means for all values of n, if it is zero, then of course that means the past is zero, future is all zero. So then yn will also be zero. So that means this expression satisfies the homogeneity. So homogeneity principle is whole. It is satisfied, it is obeyed. But that means homogeneity test positive. But what about the superposition? You have to test it. So I am giving as an assignment or homework for you. So you just test it in a rigorous method, mathematical, just a method I have just applied in the previous case. So like that, you have to do it by your own and prove that this is a nonlinear system. So I'm just giving it as an exercise to you. You just do it and satisfy yourself. Okay, like this. Time variance is already known to you, and shift variance, I'm not going to talk anything on that. It is time, or sometimes people call it a time variance, or in many cases it is defined or called as a shift, SHIFT, shift variance, or other, in our case it will be invariance, because we are mainly concerned with the LTI system, linear time invariance system. So invariance. Okay, time or shift invariance, because actually why the term shift? Because in your discrete time case or digital case, you know that the time in a first class I mentioned, within one or two classes I mentioned that the time actually in this case has lost its significance in a digital system, and it is sometimes called the shift variance. The samples are just being shifted or getting shifted. That is the thing. So, but anyway, you can also tell time variance or invariance, doesn't matter. This time word comes from the continuous time context. So in the discrete time also people use. I'm not saying they don't use. You can also use. Doesn't matter. But another name is the shift variance. Okay. But anyway, these are invariably used. It doesn't matter. Anyway, so this concept is also known to you, and if any system you also know that obeys both the linearity and the time invariance, then as a whole it is called a linear time invariant system. And mainly our course is mainly focused or concerned with this particular type or particular category of system. So nonlinearity and time variance actually is not a in that sense is not a part of this topic, sorry, the part of this course, but still in some points or in a few points I have mentioned, or in future also I will mention, because that is important just to appreciate what could happen, or if you look outside the window, what are the typical trends, or what is the typical nature that you may expect. Because if you don't have any idea, then you will be just completely blind on that. So I want that you should have some basic ideas, some basic knowledge, some basic understanding, though I'm not going for any rigorous analysis, because nonlinearity or time variance, as I mentioned, is out of the scope of this course. So, but a little bit, with a little bit examples, 1, 2, 3 examples, I'm just giving you some flavor, actually, and look out of the box kind of thing. Okay, so just again, so just for you actually, nothing else. But again, and question may come, because as a whatever I will cover in this course, whether that is there in the syllabus or not doesn't matter, but you can expect that will come in the course, in the question, in the semester. So even though nonlinearity and time variance is not there, but still, if I cite any examples or any cases or discuss something on that, then you can expect that may come. Okay. Now my next point is, suppose regarding the upsampler, na? I'm talking about the upsampler. So upsampler, upsampler is no this. Yes, this one, this upsampler. আচ্ছা, এই অবধি কারো কোনো প্রশ্ন নেই তো up to this?
No, sir.
Okay.
No, sir.
Okay, thank you. So upsampler এক্সপ্রেশন অলরেডি তোমরা দেখেছো, আমি ডিসকাস করলাম, বুঝতেই পেরেছো। এখানে আমরা একটু ম্যাথমেটিক্যালি এগেইন আমরা একটা ছোট্ট প্রুফ অ্যাকচুয়ালি করব, যে আমি অলরেডি তোমাদের মেনশন করলাম না আপস্যাম্পলারটা বলার সময়, আপস্যাম্পলার বা ডাউনস্যাম্পলার যে কোনো একটা, যে whether is this system is time varying or not, or rather time invariant or not. Actually this upsampler is a time varying system, and that could be proved, mathematically established, that can be mathematically established. So let me do it for you. এটা আমি তোমাদের জন্য করছি, কিন্তু ওইটা তোমরা করবে। এক্সপ্রেশনটা তোমরা দেখো যে তোমাদের খাতায় আছে, আমি এক্সপ্রেশনটা লিখছি না আলাদা করে, না আমাকে একটু লিখতে তো হবে, নাহলে আমি করবোই বা কি করে। Okay, suppose if x of n leads to x of nl, this is the mathematical proof, x of n leads to x of nl, suppose if, okay, then x of nl তোমরা দেখতেই পেয়েছো এক্সপ্রেশনের ভেতরে আছে y equals to the first term x of n by l. Let's x of এই যে n by l কে না আমি একটা p দিয়ে ডিনোট করছি, যে কোনো একটা লেটার n by l. Now you know that n by l has to be an integer. How can I write it p? Because n by l has to be an integer, then only the signal will exist in the discrete time or digital case. So that is why we can call it p, একটা ইন্টিজার, যে কোনো একটা ইন্টিজার না, আমি তাকে বললাম, ঠিক আছে, তাই ইন্টিজার বললাম। Now if this is the case, then time in এতে তোমরা কিভাবে চেক করো? চেকিংটা হচ্ছে এরকম, যে then x of একে যদি তুমি শিফট করো by some amount, that is n naught number of samples, if you shift it to the right hand side, then it should lead to this will also be shifted by the same amount, p minus n naught. It should happen, তাই তো, যদি টাইম ইনভ্যারিয়েন্স নেচারটাকে রিটেইন করতে হয়, and that can be written. Now you just replace this p এটা আমি জাস্ট তোমাদের কনভিনিয়েন্সের জন্য করলাম, এটা না করলেও ডাইরেক্টলি করা যায়, ঠিক আছে? এটা যা একটু বোকা বোকা লাগছে করতে, বাট এনিওয়ে জাস্ট আমি ফার্স্ট টাইম n/l মাইনাস n নট, ঠিক আছে? এটা হলো। নাও এগেইন এটা তাহলে ইনপুটটাকে শিফট করলাম বাই দিস, so the output should be shifted by this and that can be expressed like this, fine. whereas তুমি y আউটপুটের রেসপেক্টে যদি দেখো y n minus n not, how it can be written? That আউটপুটের রেসপেক্টে তুমি ভাবো, এক্সপ্রেশনটা আবার দেখে নাও একবার, look at this, আউটপুটের রেসপেক্টে তুমি ভাবছো, ফাইন? তাহলে তুমি কিভাবে লিখবে? It can be written like this, and now you see this and this, fine? And these and these two are not identical or equal, you just see. Therefore, the conclusion we can make is that the shape of the signal or the waveform is not preserved by the delay. You are giving a delay, but by giving the delay, the shape of the signal is not preserved. So it is a time varying system. So simple. Only two lines to prove, and you will get 5 marks. It is so simple. এরকম একটা দুটো কোশ্চেন তোমরা এক্সপেক্ট করতে পারো, ফাইন? তো দ্যাট ইজ দ্য প্রুফ। এই সিমিলার প্রুফটা তোমরা ডাউন স্যাম্পলারের জন্য করবে, তোমরা করে নেবে তোমাদের মতো করে। আর সেকেন্ড পয়েন্ট ইজ দ্যাট নেক্সট কোশ্চেন মে কাম whether this is a you can expect this question in the examination, even though this is a your time varying system, but still, because I have already discussed this in the class. And another question that may come, that whether that upsample is a linear system or not, upsampler or downsampler, whatever. If you take that x1 x2 and then multiply by alpha beta and then make a linear combination of these two, we'll get the same result if we comes from alpha y1 plus alpha y2 point of view, or from that direction. So it is, after all, it will be, it can be proved, and it is a linear system, so you can also do it by your own. Very simple. That proof is very simple. Now if you understood the concept, now we want to substantiate this fact, this proof, this mathematical proof, by a little example, by small example, okay, by small example, so that things will become much more clear for you. Let's do it. Suppose সহজ নেই, 0 1 2, you have this signal, 1 2 3, these 3 samples. This is suppose xn, fine? Sampling rate increasing যে ফ্যাক্টরটা আমাদের, সেটা কত? l টাকে আমরা কত নিচ্ছি? ধরো 2, ঠিক আছে, যে ফ্যাক্টরটা l. So if we have this xn, the signal may be described like it is a value sample at 0th sample has a 1 value, first sample has a 2 value, and second sample has a 3 value. For n equals to 0 it has 1, n equals to 1 2, n equals to 2 3. So this is a sample, or this is a signal, overall signal we have taken. Now if you apply this to the input of a sampler whose sampling rate increasing factor is 2, then what kind of signal we can expect? We will get কি কিরম পাবো? কয়টা ঝটপট বলে ভালো? কিরম সিগন্যালটা দেখতে হবে তাড়াতাড়ি?
জিরোতে থাকবে,
জিরোতে থাকবে, ভেরি গুড, 1
আর 2তে
2তে থাকবে 2, বেশ, 2তে থাকবে 2, 4 এ থাকবে 3,
4 থাকবে 3,
আর মাঝখানে জিরোর পরে তো 2 চলে গেল, মানে 1 আছে তো। 1 is
So
0,
1 is
very good. 1
আর
is 0
3 তে
আর
0
3 তেও 0,
3 তে
very
0
good.
3 তে 0
So দেখো L equals to 2, so L minus 1 number of zeros have been padded. L minus 1 মানে কত 1, একটা করে 0 প্যাড করা হয়েছে in between two consecutive samples, ঠিক আছে xn এ, দেখো তাই হয়েছে, ভেরি গুড। সো এই তো তোমরা বুঝতে পেরে গেছো। সো এটা আমরা পেলাম yn, ওকে। সো লেটস এটাকে এটা নাম দাও yn দাও, ঠিক আছে, yn আমরা পেয়ে গেলাম xn থেকে, ফাইন। না এখানে একটা জিনিস চিন্তা করো, এই যে সিগন্যালটা, এই সিগন্যালটা অ্যাকচুয়ালি রেঞ্জেস ফ্রম 0 to 2, so initially the xn, please note it carefully, ranges from 1 to 2, 0 to 2, that means the length is 3. That means the finite length signal whose length is equals to 3. So xn actually doesn't exist at n equals to 3, it exists up to n equals to 2. Fine. Now what we are doing, and for that I am getting this, right? Now suppose now what I'm trying to give it a shift or delay by one sample. Now if you give it a shift, that means suppose my shifted version is suppose x1n, which is nothing but a one delayed version of this, that means x of n minus 1. So what kind of signal I will get now? একে শিফট করে দাও একটা করে স্যাম্পল, এখন 0 তে কত পাবো 0, 1 এ কত পাবো 1, 2 তে কত পাবো 2, আর 3 তে 3, ঠিক আছে তো, দেখো ঠিক করলাম কি, এটা পেলাম, ফাইন। নাও প্লিজ নোট দিস 0, 0 তে 0 যেটা বলেছি at n equals to 0. Now initially যেটা বললাম, this signal exists from xn, initially exists from 0 to 2 and the length was 3. And if I ask you now, what is the length of this signal? দেখি বলতে পারো কিনা আজকে।
So 4.
Very good, 4.
4
It is from 0 to 3. This signal has no sample value at n equals to 3, but means at n equals to 3, the signal doesn't exist. But here, due to one sample delay, because you are actually shifting it to the right hand side, one sample delay at n equals to 3, now there is an existence of the signal. That means the sample value exists. So this 0, let me point out, this 0, যেটা নিয়ে আমরা আগের দিন rigorously discuss করেছি, fine. This 0 comes because of that delay xn, you are giving it is one sample delay xn. Now this 0, I think all should understand this. That is why I'm again repeating here. This 0 is actually a part of the new signal whose length is, it is also finite length, whose length now become 4. Initially the signal length of xn was 3. Now the signal length become 4 because this 0 has to be the part of the signal. So now the signal ranges from 0 to 3, that means the length is 4. Though our original range was from 0 to 2 as far as the xn was concerned, because there was no sample at n equals to 3. But what we have seen now, as we give it a delay, okay, now at n equals to 0, another sample comes. Though the value of the sample is 0, that is different thing, but at n equals to 0, another sample comes, and not only that, it actually extended up to n equals to 3, and that is why actually your window or range of window or range of vision rather actually changes. From 3 it becomes 4, from length equals 3 the length becomes 4. Okay, এই জিনিসটা সবাই বুঝেছো তো এভরিওয়ান, প্রত্যেককে বলছি কিন্তু এই জিনিসটা বুঝেছো তো। আমি
yes sir
ওকে
yes sir
ইম্পর্টেন্ট জায়গা, বিকজ এখানে একটা ফাজিনেস আছে, আমি আগের দিনই বলছিলাম। আরেকটা পয়েন্ট অফ ভিউ, আমি একটু এক্সাম্পলটা একটু পজ দিচ্ছি, আমি একটা অন্য কথা একটু বলতে চাই, আমার আগের দিন বলতে ওটা মাথায় ছিল না, এখন মনে পড়লো। দেখো, you know different types of signal representation, na? You know that because this is a graphical representation or the pictorial representation. You know the mathematical representation, you know the tabular representation, you know টেবিলে কি করা হয়, বিভিন্ন n এর ভ্যালু লেখা হয়, তার করসপন্ডিং এক্সটেন্স গুলো লেখা হয়, ভ্যালু গুলো। So different types of, another types of representation is very powerful, very মানে very concise form but very powerful. That's called the sequence representation. You know that within this bracket you have to write the sample values. So if you write the sample value, suppose for this signal, first let me write for this. So whenever I will write, how will I represent this in terms of the sequence representation? Suppose 1, then 2, then 3. To be comma dite paro in between kono byapar na, but onek jagay deয় na. So 1, 2, 3. Now if you just represent like this, if your representation exactly what is written over here, that clearly indicates, please note, though I have not given any arrow, I have not indicated any pivot element, but by default the pivot element would be the leftmost element, 1. So if whether I give this arrow actually indicates the 0th element, probably you all know. So this arrow indicates the 0th element, but even though I don't give it, by default it will be implied that the leftmost element of the value corresponds to n equals to 0. Getting the point? যদি এটা নাও দাও তাহলে কোনো অসুবিধা নেই, এটা ইমপ্লাইড, ইটস আ কনভেনশন, বাট অনেকে দেয়, ঠিক আছে? কিন্তু ধরো আমি যদি একে রিপ্রেজেন্ট করতে যাই, তাহলে ধরো আমি যদি এটাকে ইগনোর করি, সাপোজ আই এম গোইং টু ইগনোর দিস বিকজ ইট ইজ 0, সো আই এম গোইং টু ইগনোর, হাউ আই উইল রাইট 1, 2, 3. Now look at the confusion. Where if you don't give any arrow, then by default people will understand that this is the 0th element, the leftmost, which is not true. And if you want to give arrow, then where will you give it if you ignore this? Getting the point? So you have to write a 0. In this case you can put an arrow here, and if you don't if you don't want, you can't, you don't need to put it arrow, because by default the leftmost element will be treated as a 0th element. Are you getting the point? বুঝতে পারলে যে রিপ্রেজেন্টেশনটাই পারবে না করতে যদি এটাকে তুমি মানে এটা অ্যানাদার ওয়ে টু লুক ইনটু ইট, অর কি বলবো, মানে যে কোশ্চেনটা করেছি তাকে আনসার দেওয়া বা অ্যাড্রেস করা ইস্যুটাকে অ্যানাদার ওয়ে, যে তুমি রিপ্রেজেন্টেশনটাই পারবে না করতে, সিকোয়েন্স রিপ্রেজেন্টেশন ফেল করে যাবে যদি তুমি একে কনসিডার না করো। বুঝতে পারলে লজিকটা?
Yes, sir. Yes, sir.
ওকে, থ্যাংক ইউ। আচ্ছা তাহলে আমরা কোথায় ছিলাম? নাও এটা তো ডিলে দিলাম, টাইম ডোমেইনে 1 স্যাম্পল ডিলে দিলাম। নাও ইফ ইউ ওয়ান্ট টু ফিড দিস, হ্যাঁ
বলছিলাম যদি আমরা জিনিসটা n-2 মানে 2 ইউনিটস দিয়ে ডিলে করি, তখন আমার তাহলে তখন 0তেও আমার 0 থাকবে, 1এও আমার একটা 0 থাকবে, তখন তাহলে আমার লেন্থটা কি 5 হবে না? তখন
অফকোর্স 5 হবে, এখানে আরেকটা 0 দিতে হবে তোমার। হ্যাঁ
তখন সিকোয়েন্সটা
0, আমি আগের দিন পরিষ্কার বলেছি না, যদি এই 0 আর বাকি যে নন জিরোর মধ্যে 0 থাকে তাহলে তোমাকে এই 0কেও কনসিডার করতে হবে, মানে 0 বুঝতে পেরেছো, আর বাকি ইন বিটুইন। কিন্তু যদি মনে করো এরকম হতো যে এই 0-র আগে একটা 0 আছে -1, ইউ ডোন্ট নিড টু কনসিডার, বা ধরো এর পরে আছে, ধরো এখানে একটা 0 আছে 3, তোমার কনসিডার
আই এম নট কনসার্নড, ওটাতে
ইউ আর নট কনসার্ন, এক্স্যাক্টলি।
আমাকে 0 অরিজিনটার থেকে আমাকে মেনশন করতে হবে, সেটা আমার সিকোয়েন্সটা
হ্যাঁ তুমি সিকোয়েন্সটাকে মেইনটেইন করতে পারবে না, ঠিক আছে? তুমি রিপ্রেজেন্ট করতে পারবে না, তুমি তোমার যে মেসেজটা কনভে করতে চাও সেটা প্রপারলি কনভেড হবে না, বুঝতে পেরেছো? মিস ইন্টারপ্রিটেশন হয়ে যায়। ওকে, সেই জন্য আর এই অ্যারোর ব্যাপারটা একটু কেয়ারফুল থাকবে। অ্যারোটা কিন্তু দিতে হবেই এমন কোনো ব্যাপার নেই, কিন্তু হ্যাঁ ধরো মনে করো অ্যারোটা কোথায় দিতে হবে, ধরো এদিকেও কোনো এলিমেন্ট আছে, মনে করো এখানে ধরো সাপোজ এটা আমি এই এক্সাম্পলটা বলছি না, এটা আরবিট্রারি বল, ধরো এখানে 1 আছে, এখানে 5 আছে, আর তোমার 0th এলিমেন্ট মনে করো এইটা, তাহলে তুমি যদি অ্যারো না দাও, ইফ ইউ ডোন্ট গিভ অ্যারো, এক্স্যাক্টলি তাহলে বাই ডিফল্ট কি হবে? বাই ডিফল্ট এইটা এক্স্যাক্টলি এটা 0th এলিমেন্ট, সো সেটা তো হবে না, তো তোমার এগেইন রং ইন্টারপ্রিটেশন হয়ে যাবে। সেই জন্য তখন লোকজন এই অ্যারোটা ইউজ করে। বাট যদি একদম লেফট মোস্টটাই তোমার 0th হয় তাহলে তুমি অ্যারো নাও দিতে পারো, সো পিভট এলিমেন্ট বাই ডিফল্ট ওটাই হয়ে যায়।
ঠিক আছে,
এগুলো জাস্ট কনভেনশন আর কিছু। এনিওয়ে ঠিক আছে, এই পার্টটা আমি আপাতত ইয়ে করলাম, এটা তো বুঝে গেছো আশা করি সবাই যেটা আমি বলতে চাইছি। তা আমি এবারে এই জায়গাটা আসি যেটা ডিসকাস করছি। এইবারে দেখো, এইবারে তুমি ডিলে করার পর এইবারে একে তুমি ফিট করছো, এগেইন দ্য সেম স্যাম্পলার, হ্যাঁ, l = 2 ফিট করছো। এইবার ফিট করলে আমাকে বলে ফেলো ঝটপট যে এইবারে যে এটা পাবে সেটা কিরম দেখতে হবে, কিরম দেখতে হবে?
তো 0 তে 1,
না এক মিনিট লিখে নিন। হ্যাঁ বলো। জিরোতে কত? n equals to 0 তে কত বললে?
সরি 0 তে 0,
0 তে 0, বেশ। তারপর 1 এ
1 এ
ভেরি গুড 0, তারপর 2 তে
2 তে 1,
বাহ, তারপর
1, 3 তে 0,
3 তে 0, তারপর 4 এ
4 এ 2,
2, তারপর
5
5
এ
এ
0,
0,
5 এ 0,
5 এ 0,
আর
6 এ।
6 এ 3.
এবারে আমি যদি তোমাদের জিজ্ঞেস করি হোয়াট ইজ দ্য লেংথ অফ দিস সিগন্যাল? ভেরি গুড। এবার
7.
তুমি একটু আগে জিজ্ঞেস করলে উত্তর পেয়ে গেছো, এই দেখো দুটো 0 লক্ষ্য করছো। এবার
হ্যাঁ স্যার।
0 তে 0, 1 এ 0, যেটা তুমি জিজ্ঞেস করলে সেটাই পেলে। ওকে, সো এটা হচ্ছে 7। সো ইউ হ্যাভ টু কনসিডার বোথ দ্য জিরোস, ফাইন, আদারওয়াইজ ইউ ক্যানট রিপ্রেজেন্ট।
হ্যাঁ স্যার।
ওকে, তো আচ্ছা যাই হোক, এবারে এই জায়গাটা আসি, রিপ্রেজেন্টেশন তো হলো। এবারে যেটা আমরা ডিসকাস করছিলাম যে টপিকটা, যে টাইম ইনভ্যারিয়েন্স, রাইট? সরি, টাইম ভ্যারিং। কেন টাইম ভ্যারিং বলছি, ম্যাথমেটিক্যালি এস্টাবলিশ করেছি, এবার একটা এক্সাম্পল দিয়ে আমরা বোঝার চেষ্টা করছি। সো এখানে একটা জিনিস দেখো যে অ্যাকচুয়ালি এই যে সিকোয়েন্সটা পেলাম বা এই যে সিগন্যালটা পেলাম ইন জেনারেল, এই সিগন্যালটা কি is it a one sample delayed version of this? Just you check and answer. Is this signal, this pink colored signal, is a one sample delayed version of the green colored signal?
Yes,
No,
sir.
sir. No, sir.
ভালো করে দেখে বলো, এ কি ইয়েস স্যার বলে দিলে? ইয়েস, লোয়ার সিগন্যাল ইজ, আচ্ছা আমি হয়তো তোমাদের নামটা দিয়ে ভুলে গেছি, না এটা কিছু দেওয়া হয়নি, ঠিক কি, ধরো y1 দাও, এইভাবে বলতে সুবিধা হবে তোমাদের, y1 আর yn, ঠিক আছে? তাহলে আমি বলতে পারি তো যে y1n is not a one sample delayed version of yn, এই স্টেটমেন্টটা বলতে পারি তো? সবাই এগ্রি করছো তো এর সঙ্গে? ওকে, তাহলে দেখো
হ্যাঁ স্যার।
আমাদের টাইম ইনভ্যারিয়েন্সের কন্ডিশন বা ডেফিনেশন কি ছিল? ইনপুটকে যতগুলো স্যাম্পলের ডিলে দেব বা অ্যাডভান্সমেন্ট করবো, হোয়াট এভার, ইন জেনারেল শিফট করবো যতগুলো স্যাম্পলে বা টাইম ডোমেনে যতটা শিফট করবো, আউটপুটটাও ততটাই শিফট হবে। কিন্তু এখানে দেখা গেল এইটা ছিল এর x1n was the one sample delayed version of xn, but y1n doesn't become the one sample delayed version of yn. তার মানে কি হলো, lower one, that is the y, the pink colored one, now actually changed. The waveform has not been preserved. What is supposed to get is we are not getting what was supposed to get or what was expected to get. So that means, that indicates that this kind of system, that means here is an upsampler, is a time varying system. Y1n is not the same waveform as Y1. Fine. Yn and also not only that, yn to নয় তো বটে, sorry, even এর যে one sample delayed versionটাও নয়, মানে I mean to say yn minus 1, y1 of n is also yn এর সমানও নয়, তো ট্রিকি আছে, ওটা তো আমি আর বলাই বাহুল্য। So y1 of n is also not even not equals to y of n minus 1 either. So by delay we have created a distortion. We have created two zeros. This famous thing, this very popular example, যে তোমাদের একজন বন্ধু জিজ্ঞেস করেছিল আমাকে এখানে, সেই এক্সাম্পলটাই পেলেন, ঠিক আছে? দেখো, two zeros, we have created basically two zeros before the first non-zero sample. Getting the point? Two zeros you are getting, one at n equals to 0, another at n equals to 1. So if xn is an finite signal, then also, even if it is a finite signal, then also there will be some kind of distortion which is expected. if the output waveform, that is suppose our y1n will not be a one sample delayed version of yn, then I cannot say that waveform or your shape is preserved. That means, in other words, actually বেসিক ফিলোসফিটা আমি বারবারই একটাই কথা বলি সবাইকে, যে তুমি যখন ডিলে দিচ্ছ, তুমি যখন শিফট করছো, মুভ করছো, স্লাইড করছো, তোমার ওয়েভ ফর্মটা কিন্তু চেঞ্জ হলে হবে না, শেপটা কিন্তু চেঞ্জ হলে হবে না। বুঝতে পেরেছো? এটা একটু বিট কমপ্লিকেটেড, বিট ইনভলভ কনসেপ্ট অ্যাকচুয়ালি। মানে তোমাকে একটু ব্যাপারটা একটু মাথা ঠান্ডা করে তুমি দেখো, বুঝতে পারবে। আই থিঙ্ক ইট ইজ নট সো কমপ্লিকেটেড অলসো, কনফিউশন একটু হতে পারে, বিকজ আমি ওয়েভ ফর্মটা এমন ভাবে নিয়েছি যে ওয়াই অফ এন ওয়েভ ফর্মটা যদি তুমি ভালো করে দেখো, আমি আরেকবার বলছি সবার জন্য, ঠিক আছে? ওয়াই অফ এন ওয়েভ ফর্মটা তুমি যদি ভালো করে দেখো, ওয়াই অফ এন এ কি আছে? ওয়াই অফ এন এ বেসিক্যালি দেখো 1, 2 এবং 3 তিনটে স্যাম্পল আছে, তিনটে ভ্যালুজ আছে রাদার, আর ইন বিটুইন জিরোস আছে, ফ্রম n equals to 0 to 4, ঠিক আছে? তো এবারে ব্যাপারটা হচ্ছে যে তুমি যখন একে যখন তুমি ডিলে দিচ্ছ, মানে একে যখন তুমি ডিলে দিচ্ছ, ইনপুটকে যখন তুমি ডিলে দিচ্ছ, এর ওয়েভ ফর্মটা কি প্রিজার্ভড আছে? ইয়েস, ইট ইজ প্রিজার্ভড। বাট একে যখন তুমি ডিলে দিচ্ছ, দেখো ওয়েভ ফর্মটা প্রিজার্ভ নেই, মানে একে অ্যাকচুয়ালি সরি আমি আবার ভুল স্টেটমেন্ট দিলাম, একে যখন তুমি ডিলে দিচ্ছ তখনও প্রিজার্ভড হবে, বিকজ তুমি যদি একে ডিলে দাও yn-1, এখানে একটা জিরো তৈরি হবে। কিন্তু হুইচ ইজ নট এক্স্যাক্টলি, দ্যাট মিন্স এই দুটো শেপ এক হলো না, এই দুটো শেপ কিন্তু তুমি এক পেলে না, ঠিক আছে? y1n, how many samples the y1n is delayed in comparison to yn? 2 samples, whereas xn-1 should lead to y of n-1. অ্যাকচুয়ালি পাওয়ার কথা কি ছিল? পাওয়ার কথা ছিল এখান থেকে এখানে একটা ডিলে, একটা স্যাম্পল ডিলে হওয়ার কথা ছিল। It should be delayed by 1 sample, but we are getting a sequence which is delayed by 2 samples rather, ঠিক আছে? বাট যদি আমরা একটা স্যাম্পল ডিলেড পেতাম, ধরো if this was the case, suppose, then we have agreed it's a time invariant system. But actually we are not getting. y1 of n is not equals to actually yn-1, and therefore it is a time varying system. মানে ব্যাপারটা হচ্ছে ওয়েভ ফর্ম প্রিজার্ভেশন is necessary, that is true, but not a sufficient condition for the time variance. Not only the wave form preservation, but also the delay must be same as the delay of the input, otherwise that it will be a time varying system. ওকে, ওয়েভ ফর্ম প্রিজার্ভেশন তো ঠিক আছে, মানে কেউ যদি এখানে আর্গু করতেই পারো, ব্যাপারটা কিছু না যে আমি এটাকে কনসিডার করলাম, মানে এখানে যখন আমি একটা দিচ্ছি, তো আমার তো ওয়েভ ফর্ম যদি এইটুকু ওয়েভ ফর্ম আর এইটুকু ওয়েভ ফর্ম তো একই আছে। সিমিলারলি আমার যদি এইটুকু ওয়েভ ফর্ম আর এই দুটো জিরোকে আমি নেগলেক্ট করি, তাহলে তো আমার এই ওয়েভ ফর্মটা একই আছে। মানে জিরো দেওয়াতে রিপ্রেজেন্টেশনটা জন্য জিরো আমাকে কনসিডার করতে হচ্ছে, বাট অ্যাজ ফার অ্যাজ দ্য মানে শেপ ইজ কনসার্ন, শেপ তো রিটেনই আছে, কিন্তু শেপ রিটেনটা ঠিক আছে। That's why last statement I made, that it is the waveform preservation is necessary but not a sufficient. So the sufficient condition is that the number of the delay or the amount of delay should be same as well. মানে এই এক্সাম্পলটা বলে হয়তো তোমার মনে হচ্ছে, বিকজ এক্সাম্পলটা একটু কনফিউজিং, যে আমার তো শেপ রিটেন করেছে, আমি যদি ওটাকে কনসিডার না করি, বিকজ ওটা জিরো, তুমি ওই সেন্সে কনসিডার নাও করতে পারো, কিন্তু রিপ্রেজেন্টেশনের সময় তোমার কনসিডার করতেই হবে। বাট এনিওয়ে, তুমি আর্গুমেন্ট টাইপে সাজাতে পারো যে স্যার আমি যদি জিরোটাকে আপাতত এখানে ধরো আমি চেপে দিই, এটা না দেখি, তাহলে আমার এই পার্টটার মধ্যে কি তফাৎ? কোনো তফাৎই নেই। সিমিলারলি এই পয়েন্টটা যদি চেপে দিই, এটার মধ্যে যেমন কোনো তফাৎ নেই, একই। সো ওয়েভ ফর্ম প্রিজার্ভ, তাহলে এখানে আমি কেন বলতে পারবো না ওয়েভ ফর্ম প্রিজার্ভ? এখানে তো একটা জিরো আছে, এখানে মাত্র দুটো জিরো এক্সট্রা, তাহলে এটার থেকে এটা যদি ওয়েভ ফর্ম প্রিজার্ভ হয়, এটার থেকে এটা কেন নয়? দিস আর্গুমেন্ট ইউ ক্যান মেক। দ্যাট ইজ ওয়াই আমি এটা ক্লিয়ার করে দিলাম যে ওয়েভ ফর্ম প্রিজার্ভেশন ইজ ওকে। এই স্টেটমেন্টটা দেওয়া থাকে যে ওয়েভ ফর্ম শুড বি প্রিজার্ভ while delaying it, wave form should be preserved. But wave form preservation শুধু একটা কন্ডিশন নয়, মানে এটা নেসেসারি, এটা তোমাকে দেখতে হবে, কিন্তু সাফিসিয়েন্ট নয়। সাফিসিয়েন্ট হচ্ছে তোমার নাম্বার অফ ডিলে। এই এক্সাম্পলটা হচ্ছে তার খুব বড় একটা কি বলবো, তোমার এই জায়গাটাকে মানে আন্ডারস্ট্যান্ডিংটা ক্লিয়ার করবে, যে শুধুমাত্র যে ওয়েভ ফর্ম প্রিজার্ভেশনটাই যে আমার দেখলেই হয়ে যাবে তা নয়। এখানে যেমন ওয়েভ ফ্রন্ট প্রিজার্ভ হয়েছে ইন ওয়ান অ্যাঙ্গেল, ওয়ান পয়েন্ট অফ ভিউ, তুমি যদি দেখো ফ্রম ওয়ান অ্যাঙ্গেল ইফ ইউ লুক ইনটু ইট, ইট ইজ প্রিজার্ভ, বাট অ্যাজ আই মেনশন দ্যাট ইজ নট নেসেসারি, বাট ইউ হ্যাভ টু সাফিসিয়েন্ট, ইজ নট সাফিসিয়েন্ট কন্ডিশন হচ্ছে যে তোমাকে এনশিওর করতে হবে যে নাম্বার অফ ডিলেজ অর অ্যামাউন্ট অফ ডিলেজ আর সেম। এখানে দেখো যেটা সমান নয়, এখানে দুটো স্যাম্পল এক্সট্রা চলে গেছে, একটা স্যাম্পল এক্সট্রা চলে গেছে এখানে, যেটা যাওয়ার কথা ছিল একটা, এটার থেকে এটা একটা যাওয়ার কথা ছিল। যদি আমি এখান থেকে ডাইরেক্ট এখানে আসলে একটা স্যাম্পল হওয়ার কথা ছিল, এখানে দুটো চলে এসেছে, জিরো, সেটা হবে না। দ্যাট মিনস সেই জন্যই বললাম yn-1 নট ইকুয়ালস টু y অফ n, সেই জন্য এটা বললাম, মানে ওয়েভ ফ্রন্ট প্রিজার্ভেশনের রেসপেক্ট আমি প্রথমে বলছিলাম, তো সেই জন্য আমি একটু ক্লারিফাই করলাম ব্যাপারটা। তোমরা মানে বিফোর ইউ আস্ক এনি কোশ্চেন আই ক্লারিফাইড মাইসেলফ। ওকে, দ্যাট ইজ দ্য থিং। ওকে, এনিওয়ে, let me stop here for today. আচ্ছা, তোমাদের অ্যাটেন্ডেন্সটা একটু নিয়ে নি। আচ্ছা, রোল 301 30, এটা কি আদৌ আছে? 302 303
Yes, sir.
306 7 307 নেই, 307, আচ্ছা 307 নেই, 8
Yes, sir.
9 309 নেই, 10 310 310 কেউ আছো? নেই না, শুভম আছো তো মনে হলো নাকি?
309, sir.
309 না, হ্যাঁ তাই বলছি।
Yes, sir.
আচ্ছা 310 নেই, আচ্ছা 311
Yes, sir.
312 312 নেই, 313 নেই, 15 315 absent, 6
Yes, sir.
8 318 absent, 19 319, উদয়কে দেখলাম মনে হলো না?
স্যার প্রেজেন্ট স্যার।
হ্যাঁ
হ্যাঁ, স্যার, আছি, আছি, স্যার।
আমি তোমাকে দেখেছি তাই মনে হলো। আচ্ছা 319 হলো না, 320 320 absent, 321
Present, sir.
32, এই সম্প্রীতি তোমার রোল কত গো?
Sir, it's 322.
322, আচ্ছা আমরা রাহুলের পরে, তাই তো?
হ্যাঁ স্যার।
আচ্ছা সম্প্রীতি 322, ওকে। আচ্ছা 323 23 absent, 24,
Yes, sir.
আচ্ছা এবারে 401 2, এই 2 তো নেই, 40 কত আছে? 2 এর পরে 6, 406
স্যার
408,
স্যার
হ্যাঁ হ্যাঁ ঠিক আছে ঠিক আছে, 408
Present, sir.
411
Present, sir.
416 absent, 4 তারপরে কত আছো? 418
Present, sir.
আচ্ছা 9 419
ইয়েস স্যার
20 420,
Yes, sir.
আচ্ছা তারপরে কত? 425
Present, sir.
427
Present, sir.
28
প্রেজেন্ট স্যার
29 429 নেই, 30
প্রেজেন্ট স্যার।
3-1,
Present.
3-2,
Present, sir.
3-3, 4-3-3, absent. 4-3-5,
Present, sir.
3-6,
Yes, sir.
3-7,
Present, sir.
3-8, আর কেউ নেই তো?
না স্যার।
স্যার
আচ্ছা, হ্যাঁ বলো।
স্যার 401 স্যার প্রেজেন্ট দিয়েছি স্যার।
401 প্রেজেন্ট দিয়েছো? আচ্ছা দাঁড়াও।
হ্যাঁ স্যার। স্যার আসলে তখন স্যার অ্যাটেন্ডেন্সটা ব্রেক করে গিয়েছিল
আচ্ছা আচ্ছা ঠিক
নেটওয়ার্কের
আছে
জন্য।
ঠিক আছে, আমি করে দিয়েছি। আর কারুর কোনো কিছু ইস্যুস?
স্যার বলছিলাম যে কোনো ডাউটস থাকলে আপনাকে কন্ট্যাক্ট করব কি করে, লাইক ডিপার্টমেন্টে আপনি লাইক কবে কবে যান? অথবা-
ডিপার্টমেন্টে অ্যাকচুয়ালি এখন যাওয়ার তো কোনো মানে সেরকম কি বলবো ফিক্সড কোনো ডেট বা ইয়ে নেই, মানে ডিপেন্ডিং অন দ্য রিকোয়ারমেন্ট বা ইয়ে যেতে হয়। তো তুমি একটা কাজ করো, ওরম ভাবে করতে হবে না, তুমি মোটামুটি যে ডাউটস গুলো থাকবে বা এ থাকবে তুমি একটু নোট ডাউন করে রেখো।
আচ্ছা স্যার।
পরে একটা সময় যদি আমি কোনোদিন এরম ভাবে যাই, আগে থেকে কোনো প্রি প্ল্যান থাকে আমি জানিয়ে দেবো, অথবা তুমি অনলাইনে ক্লাসের পরেও আমাকে জেনে নিতে পারো, ঠিক আছে? ডিসকাস করে নিতে পারো কোনো একটা
আচ্ছা,
দিনে বসে। আর একটু কিছু পড়িয়ে
Sir,
টড়িয়ে নিই।
4 to 9.
হ্যাঁ বলো কি বলছো?
4 to 9 present, sir.
4-9, দাঁড়াও, 4-9, ও সায়ন,
হ্যাঁ স্যার।
আচ্ছা ঠিক আছে। আচ্ছা আমার তাহলে নেক্সট ক্লাসটা কবে হচ্ছে?
স্যার ওয়েডনেসডে, কামিং ওয়েডনেসডে।
কামিং ওয়েডনেসডে মানে কত তারিখ পড়ছে? 8 তারিখ, তাই তো? 8 তারিখ,
হ্যাঁ স্যার।
8 তারিখ। টাইমটা কটা ছিল?
2:30।
2:30, ঠিক আছে তাহলে আমরা সেই সময় মিট করবো আবার। ওকে ঠিক আছে, থ্যাংক ইউ।
ওকে স্যার।
থ্যাংক ইউ স্যার।
থ্যাংক ইউ।